Welcome. Today we shall be looking into some of the more techniques about removal of the nitrogen from the natural gas. In this particular lecture, we shall be looking into adsorption, membrane and gas hydrate modes of separating the nitrogen from the natural gas substance. So we shall be learning about these three methods: adsorptive separation, membrane separation and hydrate separation. So what we have learned earlier, there are 5 methods. These two, absorption, cryogenic distillation, we covered earlier, and in this lecture we shall be covering up these 3 types of nitrogen removal methods. Now coming to adsorptive nitrogen removal, so first we see that the adsorption is the choice after cryogenic distillation, and in this case we use generally pressure swing adsorption, or what we call PSA, to remove high amount of nitrogen, which is the adsorbate, at a low heat of adsorption, and the adsorption pressure is about 10 to 100 kilopascal, and the adsorption temperature varies between 273 to 323 Kelvin. The heat of adsorption is between 15 to 22 kilojoules per mole. So these are some typical figures for carrying out adsorption, and the heat of adsorption is significant because this decides that how much energy we would need for the regeneration of the spent adsorbents. So the principle of this adsorption separation is that this is the figure we can see here, that we need at least 2 beds for carrying out PSA depending on the time of adsorption and for the bed to get saturated and the time of regeneration. So here we see in the figure we have 2 beds here, and all these valves have been given different symbols. Like these filled valves are showing that there is the flow going on, and these empty things are showing that these are closed. So in this case we understand that when one bed is undergoing adsorption, the other bed has been taken for regeneration. Now if we trace this particular feed, we find that the feed is coming, suppose it is coming, and suppose in this case it will be coming through this unfilled or this blank valve. So it will be coming through this, while this particular thing is kept closed. So it will go through this, and then it gets adsorbed over here, and then it comes through this particular valve and goes out the product. Now suppose this particular bed gets exhausted, then what we have to do? We shall be switching off this, so we shall be closing this valve and we shall be opening this one. Now the same process will go, the feed will now come here and it will go to pass through this bed and it will go for the production. Now while in case of regeneration, what is happening, that this particular bed is undergoing regeneration. So what is happening, that we are putting some kind of a maybe hot stream through this bed, and this bed, from these adsorbents, the adsorbed solute, for example in this case if we have adsorbed nitrogen, the nitrogen will be carried over from this particular adsorbent bed and this will be taken out, and then this bed will be ready for the adsorption. And in this particular figure what we see is that how the loading capacity or the adsorption capacity varies with pressure, and here we see that we are comparing this PSA and TSA. Now suppose we have this particular red line in which we are showing that how this taking place at one temperature and this is taking place at another temperature. Obviously, since adsorption is favored at lower temperature, so this T adsorption must be lower than the T desorption. So suppose we start initially from this particular point, that means at this particular pressure, at this particular temperature. Now if we are carrying out PSA, that means we are reducing the pressure. What we have to do for that, we go to like this, so that we are going to at the same time, this is done isothermally, so that we are going on the same isotherm, but we are just reducing the pressure so that we can find that the loading of the bed decreases. So that is how we are able to regenerate the bed. On the other hand, if we want to use TSA, then what we need to consider is this: at the same pressure, we cool down the heat of the bed, and then we go to another isotherm, and that is at, we find that this T desorption is more than T adsorption. So that means this particular vertical line shows the TSA, that means the thermal swing adsorption way of regenerating the catalyst adsorbent, and this shows this PSA, that is the pressure variation, how we regenerate the adsorbent by varying the pressure. So these two things can be carried out in this pair of beds. Now, in case of nitrogen removal, what we find that mostly the adsorbents show equilibrium selectivity for methane over nitrogen. That means methane is selectively taken up by the adsorbents. Of course, it depends on the type of adsorbent, but the most of the adsorbents show that more selectivity towards methane, that is nitrogen is purged out while methane is retained. And molecular sieves and titanosilicate show kinetic and equilibrium selectivity for nitrogen. We shall learn in a while what is kinetic and what is equilibrium selectivity. Now, narrow pore size distribution of adsorbents, as we learned earlier, that pore size distribution is very important. That decides that how selectively we can adsorb the various solutes. So in this case, we find that the diameters of the nitrogen and this methane molecules are very close, about 3.64 angstrom and 3.8 angstrom. That is why we find that the pore sizes of the adsorbent have to be very, very carefully made, so that we can differentiate between these two types of molecules which have very close diameters. So that is why we find that in this case kinetic and equilibrium selectivity is preferred rather than steric selectivity. So that is now we see that the mechanisms of the adsorptive separation. So first we have the thermodynamic equilibrium mechanism. What it means is this, that it shows the differences in the adsorbate and the surface interactions and or adsorbate and packing interactions when the system reaches equilibrium. That means we allow all the solutes to reach equilibrium and then measure their respective concentrations on the adsorbate. So depending on the adsorbate-adsorbent interaction, various solutes will be adsorbed to different extents at equilibrium, and this extent, the difference in the extents will determine the separation and the selectivity of the various solutes by the particular adsorbent at equilibrium. Then we have another mechanism, that is the steric mechanism. In this, what we do, that differences in the size and or shape of gas molecules dictate. That means the molecules which are larger than the pore size will not be allowed through the adsorbent, whereas those molecules which are smaller than the pore size will be allowed to enter the adsorbent particles and then get adsorbed. So this is called the steric mechanism. And lastly, we have the kinetic mechanism, in which the difference in the rates of diffusion of the various solutes through the adsorbent particle determines their separation. That means in this kinetic separation, all or some of the solutes are allowed to pass through the pores of the adsorbent, but depending on the rate at which they are traveling inside the pores will determine their respective adsorption capacities. Now, next we have this adsorption NRU, that is the nitrogen removal unit. In this case, we find that this is the kind of characteristics which have been found, that this curve shows the equilibrium adsorption capacity of carbon dioxide, methane and nitrogen at 298 Kelvin on zeolite 13X. This zeolite 13X is one of the adsorbents. On this particular adsorbent at this particular temperature, this is a typical curve which have been shown for these three components, and what we find that this zeolite 13X adsorbent adsorbs carbon dioxide preferentially in comparison to methane and nitrogen. That means from this we conclude that carbon dioxide, if we want to remove carbon dioxide from natural gas, then we should go for this zeolite 13X, and once carbon dioxide is removed, then we can see that next is the methane. That means this 13X, zeolite 13X adsorbs methane more than nitrogen. So then what we find, that this particular, after removal of carbon dioxide, this particular adsorbent may be used to remove the methane from the nitrogen. Here in this particular table, we have listed some of the commonly used adsorbents for the nitrogen removal, and here we find that different references have been given here, and we find that various these from which are the vendors who can supply these particular kinds of this adsorbent, and we find that some are metal based, some is activated carbon, then titanyl silicate, then zeolite, and all these things, and we are finding that which of the components is selectively adsorbed on this particular adsorbent. Like for example, in this metal based adsorbent, carbon dioxide is the more adsorbed than methane. Then in activated carbon also, carbon dioxide is preferentially adsorbed to methane. Then in this we find that this particular zeolite, this is this nitrex, soluble nitrex, this particular thing we find that in this case methane is selectively adsorbed to nitrogen. So this way, by looking at these particular figures, we can find out that which adsorbent to choose from, and here in this particular column we are shown the kind of the capacities of these various kinds of adsorbent beds. And here are some more of these adsorbents. So these adsorbents, these things are very exhaustive list of the various types of adsorbents that may be considered for the removal of the various types of impurities from natural gas like carbon dioxide, nitrogen, etc. So these come handy whenever we are supposed to design an adsorption column for the removal of these particular impurities from natural gas. Now next we come to the membrane nitrogen removal units. Now these membrane units are limited to pre-treatment and compression of feed stream to produce the desired driving force, and natural gas is generally at sufficient pressure, but still we may need compression for membrane separation, as we learnt earlier that the separation through membrane depends on the difference in the partial pressure of the particular solute across the membrane on the, that means the permeate side and the retentate side, and we know that if we increase the pressure at a given mole fraction, the partial pressure of the particular solute will increase. So we need to pressurize the gas to be separated at very high pressure, and in case of natural gas, even though natural gas comes out from the earth at sufficiently high pressure, still more pressurization may be needed if we take it for membrane separation. And the membrane performance is characterized by the permeability and the selectivity. What they mean? That permeability refers to that how much the membrane will allow some particular solid to pass through, and selectivity means that preferentially which of the solutes will be allowed to pass through the membrane. And these membranes are not commonly used due to low selectivity of similar sized nitrogen and methane. That means if we want to separate nitrogen and methane, then generally this is not done much, and the selectivity we find that is less than 3 for glassy polymer membrane and less than 5 for rubbery polymer membranes, and addition of some inorganic fillers is done to increase the selectivity by making the mixed matrix membrane. So we use some fillers so that we can overcome this kind of small selectivity of the membranes. Now we use asymmetric inorganic membranes made from silica, zeolites and carbon molecular sieves, and unlike these organic membranes, these membranes can operate at high temperatures. So we find that organic membranes may get destroyed at high temperature, so the inorganic membranes are used. And asymmetric, as we learned earlier, that asymmetric means we have a very thin skin of the membrane which is supported by a quite porous and thin support. So that is asymmetric membrane. So these kind of asymmetric membranes are used for the separation of these impurities. And the design of this membrane NRU is determined by the membrane capacity, that is dictated by the membrane material, then the feed gas pressure, the kind of contaminants we have in the feed gas, and the desired level of purity of the product. There are some operational issues in the membrane which sometimes restrict the use of the membrane for the impurity separation. In this case, we find loss of selectivity and separation performance may occur over a long period of time. Why? Because of basically two reasons. One is plasticization, that means the membrane polymer swells, and this swelling of the membrane is caused by the carbon dioxide, water and other aromatic hydrocarbons which are present in the natural gas, or the degradation of the polymer membranes. So, this leads to the loss of the selectivity and the performance of the membrane. And to prevent the plasticization, what is done? Some cross-linking of the polymer networks and use of some fillers. So, these are something which are taken. We are not going to detail of these things. So, we chemically treat these membranes so that we can prevent the plasticization of the membrane. And also we need to go for pre-treatment of the feed gas so that we can remove any kind of contaminants which can enhance the plasticization. So, like for example, we can remove the carbon dioxide or water and then alleviate fouling by removing the oil mist and the particulates. As we learned earlier, fouling means the deposition of undesirable components on the membrane surface, which will prevent the diffusion of the solutes to the membrane. So, we need to prevent the fouling and then prevent the condensation of the heavier hydrocarbons and water on the membrane surface. So, here we find a typical membrane module that some low pressure gas, say about 10% nitrogen, is coming through this, and we find that it is first going to, so typically it is first going to one membrane module, and in this case the permeate is taken out as a pipeline gas which has less than 4% nitrogen, and the retentate is again taken to next membrane module, and here we find that we can get the fuel gas, and the permeate from here, this is about 10 to 15% nitrogen, is sent back to the feed stream, and again after this compression and after this filtering, again we send it back to the membrane modules. So, this is a typical membrane separation unit for this nitrogen removal. And here we find that the membrane performance which has been plotted with the nitrogen permeance against the nitrogen to methane selectivity, and what we find here is this, that as the selectivity increases, the permeation decreases. That means for an increase by an order of magnitude in selectivity, permeation for nitrogen decreases by 4.5 orders of magnitude, while for carbon dioxide decreases by 2.6 orders. That means order of magnitude means, suppose we go for 10 times increase in the selectivity, then what we find that the permeation decreases more rapidly than the selectivity for the carbon dioxide, for the nitrogen than for carbon dioxide. And here we find what are the various kinds of membranes which have been put: silica membranes, polymer membranes, then some hollow fiber. So, we find for different types of membranes, we find different types of this relationship between the selectivity and the permeance, but the overall trend is that the selectivity decreases with an increase in the permeance. And that is why what we do, we need to do multi-staging to treat the natural gas for nitrogen concentration between 3 and 30%. So, when we have, sorry, 4 and 30%, when we have this kind of amount of nitrogen, we go for multi-staging. That means we use a number of membrane modules. Lastly, we come to the another thing, which is the nitrogen rejection by hydrate route, and use of hydrate has been done for separation since 1930s. That is, it is not a very new process, and hydrates can be used to produce lean gas stream with respect to hydrate forming gases. That means hydrate forming gases are many. We have learned that carbon dioxide, H2S, then water, if they react with this, then we get hydrates. So, with respect to these hydrate forming gases like carbon dioxide, nitrogen, H2S, etc., this hydrate route may be used to get a leaner gas. Leaner gas means which will be having less amount of these particular impurities. So, in case of carbon dioxide, nitrogen and methane mixture, carbon dioxide is preferentially forms the hydrate, and use of high pressure for hydrate formation makes this process uneconomical, because we know that hydrate is formed at high pressure and low temperature. To make this particular process possible, to separate carbon dioxide or nitrogen, we need high pressure, and this high pressure has its own challenges. So that is why it makes the process uneconomical, and a typical natural gas forms hydrate at pressure more than 30 bar and at a temperature less than 20 degrees centigrade. And to make the or to facilitate the hydrate formation, some kind of hydrate promoters are sometimes used to reduce this formation pressure. But we have to understand that whenever we are using some promoter, that means we are also adding some kind of impurity to the system. So still then there are no commercial scale process operation for NRU, and gas liquid contact is very important for hydrate formation, because unless the gas comes in contact with water, we cannot form the hydrate. So it is very important to ensure that these two phases get properly mixed in a particular chamber. So in this case, bubble columns and stirred tank reactors are used. Hydrate formation is exothermic. That means it is accompanied by release of energy. So to remove the heat of hydrate formation, what we need to quickly take out the heat, and for that various devices may be used, and one of them may be a fluidized wet heat exchanger, and this kind of heat exchangers prevent the hydrate deposition and increase the internal heat transfer coefficient. So fluidized bed do not allow the solid hydrate to remain inside the particular chamber. And here is a typical flow diagram for this hydrate formation, that here we have the feed gas, and in this particular chamber we are having the hydrate formation, and we find that if carbon dioxide forms hydrates, then this outgoing gas will be richer in nitrogen, and then this particular thing will be richer in methane, and this will be going to a pump, and it will go through this hydrate melter, and it will be taken to this particular chamber, where we shall be separating out the water, and the water gets, that means we are basically heating up this melting means we are heating up the hydrates, and to separate out the water from the methane, and in this exit gas we are having the methane rich exit gas, whereas the water comes down and is recycled to this particular hydrate forming chamber. That means in this particular system we are first forming the hydrate, and then next time what we are doing, we are recovering the water and sending it back to the hydrate column, and this recycling is enabling us to reduce the use of the fresh water. We are able to recycle these things. And here are some of the references which we refer to get more information on this particular topic. Thank you.